Good evening and welcome to this Window to the Stars, Stars for Schools video. Today we're going to talk a little bit about the Lady Eleanor Holles students' project on survivability of life on Earth when things change on the Sun. The Sun, of course, was born 4.5 billion years ago, and it still has many billions of years to go. But the question is, how long can life survive on there? So what we're going to do is look a little bit at some of the ideas and concepts around this and see how they can fit in nicely with the project. Now, I thought the first thing we'd do would be to run Window to the Stars and just make a model of the Sun. Now, I've pre-made these models because it takes a few minutes to do it, and but they're easy enough to make, and I'll explain how to do that in here. And you've already indeed done some of this, which is fantastic. So let's switch to Window to the Stars. You probably recognize Window to the Stars. This is the standard Window to the Stars. And what I've done here is to run a track. This is the evolution of a star with a metallicity of 0.02. So that's pretty standard. That's what it comes out with by default when you run it. And I can label the beginning of it. There we go. Z is 0.02. Now that's a little bit higher than the Sun we think now, but it's pretty close. What that means is that 2% of this star, which is a one solar mass star, so the same mass as the Sun, it means that 2% of it is not hydrogen or helium. So this is 2% is made up of everything that is iron or oxygen or carbon or nitrogen, all these other heavier elements. So we'll stick to that for now. Now, one of the things that you probably want to consider is what happens as the Sun gets older. The Sun's luminosity is not a constant. It starts down here where it's born, and then it evolves this way as it gets older and older. Now, the question is, you have to think, how bright can the Sun get before life on Earth is impossible? Or indeed, you could ask the question the other way around. How much dimmer could it have been in the past? And life would have been impossible. So that's quite an interesting question. So what I'm going to do is to have a look and find the region on this plot where the luminosity of the Sun is no longer compatible with life on Earth, or roughly speaking. I mean, there's no exact answer to this, but it's a rough idea. And what I'll say is, well, let's consider maybe plus or minus 30%. Okay, so if the sky is 30% dimmer or 30% brighter, it's then too dark or it's too light for life as we know it to exist. And I know that's roughly what we'd expect. Now, I've also chosen 30% because we'll see that the scale of the luminosity here is what's called a logarithmic scale. Now, 30% on a logarithmic scale is particularly simple. I have here my calculator. And you can see that if I take the logarithm here, so this is the logarithm in base 10, because we work in base 10, all of our numbers we have 10 fingers with the thumbs. So that's base 10. If I take the logarithm of base 10 of 1 plus 0.3, that's 1 plus 30%, 1.3, then I get about 0.1, 0.1, 1 and a bit. So what I'm going to do is to find the region of this plot which is closest to 0.1. Now, remember this. Now we have one solar luminosity. What's the logarithm of 1? Let's type this in. 0. So 0 is the Sun. So the Sun is along this line 0 here. That's about this point here. Now, I can also label these with the ages. And so you can see down here, you start at 0 at this end, and then you've got about 4 billion years, or 3.9 billion years. And then 9.5 billion years is here, and it hasn't moved very far. Not much has happened. It's only after the hydrogen runs out in the core that it starts to go up the giant branch, and that's when it very quickly rises up here. And you see the numbers are the same. That's because to 2 decimal places, it's the same age. It does get older as it goes up here, but very quickly. But what we're going to do is zoom in on this corner down here, which is where we're existing at right now. So if I zoom in there, you can use the mouse to zoom. You see what we've done now is we've zoomed in on this region. But remember, we wanted 0.1. So we want to go with 0 up to 0.1, which is about here with the mouse, and also 0 down to minus 0.1. So we want to look at when the sun was dimmer. So let's zoom in again down here and keep doing this until we get to roughly plus or minus 0.1. There we go, that'll do. That's close enough. You can see now minus 0.1 here and plus 0.1 here. 0 is this line here. And you see we are at around 4.5 billion years. So the code is working. This is a good thing. So the star starts its evolution up this track here. And this is around 4.5 billion years. So this is us now. And let's say that everything between plus or minus 0.1 on this scale, so that's plus or minus 30%, that's from here down to here, could support life. So you see, life could be supported pretty early on in the evolution of the sun, going by this definition. Down here is just after 1 billion years. This is 865 million years. You could support life pretty well down here. And indeed, that's probably roughly where life started. Maybe single-celled life forms, sure, but it's around that time. Somewhere between there and there is roughly where life started. And then it gradually got more and more complex. And then as we got to the amount of light that we have now, everything was good. How long, though, can the Earth continue to support life? And let's assume we can go up to plus 0.1 on here. That'll give us a few billion years more. But after that, we're in trouble, because the luminosity of the sun will be so strong that the Earth will literally boil. The oceans will boil first, and then eventually the Earth itself will probably melt, and that's not good. That's not a good thing. Certainly the atmosphere will be boiled off at some point as well when the luminosity gets too large. So that's going to be a problem for us. It's probably not something to worry about right now, but it's something you probably, if you were planning to live for a few billion years, it's something that you might want to consider. Now, the other thing you can see here is that while the star starts down here at low luminosity and it increases up here and gets more and more luminous, it also moves from right to left in the Hertzsprung-Russell diagram. What that means is it's going from red on the right to blue on the left. You can't see it so much here because it's not a huge difference, but if we zoom back out and grab the whole diagram, you see on the right here is red, which is cooler, and on the left is bluer, which is hotter. So what's actually happening, if we zoom back in down here, what's happening is the star is getting hotter, a little bit hotter with time. And you might think what that means is that the star is actually going to give us more ultraviolet. Because if a body is hotter and bluer, that means that it has more short wavelength light. And that tends to be more than in the ultraviolet. Now, those of you who've been out on a day where the ultraviolet is strong, that is like last weekend when it was very sunny, you know you can get sunburned very easily in that. And that is a potential problem for these stars. However, one other thing I've looked at here, if I just reset this and go back to where we were, turn off the time labels, I've also run some tracks which are at a different metal content, what we call the metallicity. So that's a different amount of heavy elements, everything like oxygen or iron, things like that in the star. And I've made them in the layers that Windows the Stars has. And I've made several of these here. I've got the solar one, which is 0.02. That's the one you're seeing now, because that's the one ticked on. But I've made some at 0.03, that's higher metallicity. I've also made them at lower metallicity, so 0.01, 0.001, and 0001. I have to make sure I can count that many. So these stars are much lower metallicity than the sun. So let's plot a star that is lower metallicity. Let's go for the half solar, which is 001. We can plot that at the same time, and now you see we have two tracks here. And they're not on top of each other. And the reason for that is that stars that are lower in metals tend to be hotter. And you can see that. The star has shifted to the left in this diagram. So it's much hotter than it was before. Now, if we drop the metallicity again by a factor of 10, we can see again, the star jumps quite a long way this time. Goes from over here to over here. And now you can see the color is much bluer. Now, these colors are not real colors because we can't have a real star on the screen, but they're as close as I can get to real colors. So they tell you pretty well how blue these stars are, and that is a lot more blue. And if we go to the 0.0001, that's bluer again. It's over on the left here now. And it's brighter. So these stars make it much more difficult for life to survive on somewhere like the Earth at the distance of the Earth from the sun. So these would be a real struggle to survive. Now, that's at least what we thought. There was a wonderful paper, which I'm about to show you, if I can find it. There's this paper, which is in Nature. So you can have a look. You can go find it yourself, by Shapiro et al. And they talk about whether ultraviolet from stars that are different metal contents are actually more or less likely to be good for life. And this goes completely opposite to what I've just explained to you. And the reason is, they have a wonderful diagram a bit further down. I can show you. So in this diagram here, you can see the flux. That's essentially the power per unit area hitting the Earth as a function of wavelength for different metal contents. So 0 here is the sun. A positive value is more metal. So that would be stars that are cooler. And the negative is for less metal, which we thought should have more ultraviolet. And indeed, it does have more ultraviolet. You see that from this. So you get more flux here, which is less than 400 nanometers. That means it's ultraviolet. So ultraviolet is all 400 nanometers or less. And you see the blue curve is at the top, and that's the most negative here. And so that's the most metal poor. So you would think that's the most dangerous for life because there's more ultraviolet. But if you start learning a little bit about chemistry, which I must admit I am completely ignorant of, you have to look at a diagram like this, where the ultraviolet, here the UVC and the UVB, the UVC manufactures your ozone, which is the protecting chemical in the atmosphere. You get it manufactured much more at lower metallicity. So you actually have more protective ozone in the top of your atmosphere in stars, well, when you have stars nearby that are metal poor, which is the opposite of what I used to think. So I've learned something tonight. I've learned a lot about how life is complicated, and it turns out that possibly lower metal content might be better. So I thought this was very interesting, something for you to follow up on, perhaps. Okay, now probably the next thing you might want to look at is what happens when the star gets very old. So here, if we turn off the other metallicities, we go back to the solar case. This is the solar case, and you can see what happens is the star eventually gets very red, which is as you'd expect. Now, what does that really mean? It actually means that the star is getting bigger. Now, you know, because you've been using Window to the Stars, you know how to plot things to see whether the star is getting bigger. So let's look at this one. This is the radius of the star. You see log r, it's logarithmic again, but we can actually plot it without the logarithmic scaling. What we do is then we say 10 to the power of it. Now, you can do this because logarithm and 10 to the power are the opposite of each other. They're inverse. So if you apply them both, you just get the value of the radius, which is great. Now, fortunately, Window to the Stars knows this. So you can just plot the radius here of the star in solar units as a function of time. Now, for most of the star's life, this is the hydrogen burning main sequence, nothing really happens. It sits around 1 solar radius, which is what it is now. However, when it runs out of hydrogen in the core and the hydrogen burning shell around the core becomes dominant, the star expands. And you see here it becomes nearly 160 times as big as it is now. Now, this is problematic for the Earth because the Earth sits at 1 astronomical unit from the sun. And an astronomical unit is, I'll show you the Wikipedia page. The astronomical unit is defined as this many, zoom in a bit here, there we go, this many meters, which is 149 and lots of other zeros. If we scroll down a little bit, you see here it gives you the unit in other units. So in units of the radius of the sun, it's around 215. So what that tells us is the Earth is 215 solar radii from the sun. But if the sun then expands to be nearly 200, it's up to 170 or so here. If it's nearly 200 itself, the surface of the sun will then be exceedingly close to the Earth. Now, you can imagine in your project you've been calculating how much flux hits the planet from the sun. Well, you can imagine if the sun is right next to the Earth, that flux is a lot. And that is certainly a problem. And that's probably something worth investigating. One other thing to look at is if we turn back on to the logarithmic scale, is the reason we use a logarithmic scale here is because, if I go back to that, there we go. Now you can see the logarithmic scale is back. You can see the log 10 is here. But if you do that, you see you can see that increase now. The logarithmic scale is brilliant for looking at numbers that change by many, many orders of magnitude. So they go from very small to very large. And that's why we use logarithms. That's why on the HR diagram, there are also logarithms. And you're forced to use them. Otherwise, everything would look like it's 0 except on the giant branch. And that's not very useful. So that tells you everything about the radius of the star. Now, one thing you can also do is you can plot the radii on your Hertzsprung-Russell diagram. So there's a radii button up here. If you press that, it will then draw lines of constant radius. So down here, near where the sun lives, which is now is there, the radius is just a little bit more than 0.887. It's actually 1, of course. What is the radius of the sun now? It's 1 solar radius. But that's slightly more than 0.887. But you see, as it gets older and it evolves up this track, the radius increases. It starts crossing the line here, it's 4.9, and then it goes to 8.7, and it gets bigger and bigger and bigger. Now, what stops the sun expanding is when it ignites helium in the core. And in this particular model, that's right here. We can look at our other metallicities as well, if I turn those back on. There we go. And you see they ignite helium at slightly different points. Usually when the metallicity is lower, the star is more compact, so it's less likely to swallow the sun at that point. However, of course, you still have problems because the star will also be very bright and it'll be very hot compared to our sun, which will be over here. These ones are bluer on the left here when they have less metal, which means they're more likely to fry the planet, which is also not a great thing. So one other thing you might want to look at is the rotation rate of the Earth and how that changes with time. Now, that's not something to do with the sun as such. That's more to do with the moon. But I found a wonderful paper here by George Williams. This is it's in Reviews of Geophysics from February 2000. I'll put a link to this on the page. This talks about how the number of hours per day changes with age. So the Earth has not always had 24-hour days. It's in the past, the length of the day was quite different. And he has a nice diagram here showing how the moon, which is sitting over here, interacts with the oceans on the Earth, and it distorts the Earth. And in the process of this, the Earth tries to spin at the same rate as the moon goes around it. But of course, they're not quite the same, which means that you have gradual slowdown of the Earth. Now, you can imagine if the Earth slows right down in time, what will happen? Then we're in trouble, because if the Earth slows right down, days get longer and longer, then presumably the hot side of the Earth will be hotter and the cold side of the Earth will be colder, because if you can imagine, if you had very fast spinning, then it would be the equivalent to sort of very short nights and very short days, and they wouldn't have long to heat up or long to cool down, so they'd sit around the same temperature. Whereas if you have long nights, then of course it will get very cold, and then you have a long day, and that means it can get very hot. Now he's got this lovely plot here which shows the age is on the x-axis here, so now is over here on the right. You see now, how many days do we have in a year? Well, it's around 365, so that's this cross here. So that's absolutely fine. But in the past, there were many more days in the year, which means the days were shorter. So we've been slowing down with time, and presumably this will continue. It's quite complex to explain why, but it's something you can look into. You can have a read of this paper. There's various sources online. You can find explanations for this. So that's something else you should look at, because it's not to do with stellar astrophysics, but the tides do affect stellar astrophysics, because 1/3 of all of our tides roughly is from the sun. So the sun is extremely important for our tides. The moon dominates the tides, but the sun is also important for the tides. So hopefully that's given you a few ideas for things you can talk about when you're doing your projects on whether we can survive on the Earth and how long we can survive for. Thank you very much for listening.